Welcome to this webinar, Cluster Computing, Scaling MATLAB Applications. My name is Gerardo Hernandez, and I am an application engineer here at MathWorks. There are three topics I want to cover. Workflows that can benefit from cluster computing with MATLAB, the steps you need to extend your MATLAB workflow to a cluster, and the licenses you will need to scale your MATLAB applications. MATLAB Distributed Computing Server makes cluster computing with MATLAB easy and accessible. Distributed Computing Server takes workflows developed with Parallel Computing Toolbox and extends them to hardware beyond the desktop. Before we talk about extending our MATLAB applications on the cluster, let's review how easy it could be to use the Parallel Computing Toolbox to speed up our applications on our desktop machines. And I want to do that via this simple example where we're doing a parameter sweep. In this example, I will show you how you can speed up a parameter sweep for a system of ordinary differential equations. And don't worry, if you're not working with parameter sweeps or ordinary differential equations, the important aspect of the example is the workflow. What we have here is a cantilevered truss. We can modify the number of truss elements, the height of the truss, or the cross-sectional area of the truss elements. And what we want to do is we want to investigate what the maximum deflection would be under a given load. And we're going to go through the different combinations of values using a for loop, and then we're going to parallelize it using a par4 construct. Let's go to MATLAB to see how this works. Okay, so we have a function called param sweep that takes certain input arguments, where we're going to specify the number of horizontal segments that we are going to consider, the different heights, and the different cross areas that we're going to analyze. So the input arguments to this function are the different values of the parameters that we want to consider. And what we're going to be doing is we're going to use a for loop to go through every single one of those combinations of values. And we need to check first if the model that we're going to use is valid. There are some assumptions that have been made, so we have to make sure that those assumptions are being met before we actually solve it. But if the assumptions are met and the model is considered to be valid, then we're going to record the peak values of the simulation. And we're going to be doing this for every single combinations of the values. We're going to be recording that value. And at the end, we're going to time how long it takes with the tick and the talk that we have here, and we're going to visualize the results. So let's take a look at how we can actually get that done. Let me start by initializing the values of the parameters that we're going to use. And let's call the function that we're going to use. So it's parameter sweep. We're not really interested at this point on all the output this function is going to provide. We want to see how much we can gain by parallelizing this algorithm. So let's just run this. It shouldn't take too long to run. So the algorithm is building the finite elements and is building up the stiffness matrices, and then is solving the system of ordinary differential equations that results, and storing the peak value for each one of the simulations, and then it's going to plot that result. So we can see the curve here with the maximum deflection for the particular cross section for different values of the number of horizontal segments and different heights. And more importantly, we can see that the algorithm takes about 18 seconds to run. So now what we want to do is we want to parallelize this algorithm to see if we can take advantage of the fact that the iterations are independent from each other. So the first thing I want to do is I want to start my parallel pool. You guys know that in the newer releases of MATLAB, it is no longer necessary to manually initialize or start the pool of workers, but it's a feature that I still have control of. So if I wanted to do that manually, I can do that either interactively or programmatically. The second thing I want to do is I want to modify this for loop because I know that the iterations are independent from each other. So I'm going to parallelize this by converting that regular for loop into a parallel for loop. So now that I have done that, let me save this first, make sure that I'm running the latest version, and let me run this algorithm again. So now, because I have a dual core machine on my local system, I'm using 2 cores. With the parallel for loop, I should see a performance improvement in there. So I get exactly the same result, and I can see that I go from 18, something like 18.6 seconds to 11.4 seconds. So I get a significant speed up just by modifying the for loop. Now that I have my parallel code working on the desktop, I can easily run it on a cluster just by changing my cluster profile without the need to make any changes to my code. So let me show you, now that I have this parallel code, how can I run it on my cluster. Now that I'm in MATLAB, all I have to do is go to my Home tab, look for the parallel menu, and select the cluster I want to use for this simulation. In this particular case, I'm going to use a cluster called Speedy to run the simulations. And just as before, even though I don't need to start the pool of workers manually, I can do that. I did it interactively before, so let me do it programmatically now so that you guys can see that you still have control over the process. Now, this cluster Speedy has 32 workers in it, but this simulation doesn't require that many workers. I want to be a good citizen, so let's say that I only want to use 16 workers to run it. So I'm going to initialize my pool of workers, and once my workers are up and running, I'm going to run the same algorithm again. So let's see if we can do any better. Okay, my workers are up, so let me just run my algorithm again. So MATLAB is automatically going to analyze the code, it's going to transfer the data to the workers, it's going to see if there are dependency files. If my MATLAB function is using other custom functions, it's going to check what the dependencies are, and it's going to send all those files that are required on the cluster side to be able to run my algorithm. It's going to send them along to the cluster side so that I can get the work done. So we can see that we get the exact same solution that we were getting before, but now we're getting it in just 4.7 seconds. So we're getting a significant speed up by having additional MATLAB workers at our disposal. I just showed you a simple interactive workflow, but there are many other workflows that are possible with the MATLAB Distributed Computing Server, including scaling up to a larger number of workers for a single application using GPUs and multiple GPUs on the cluster side, and even distributed memory applications. Well, now that you have seen how easy it can be to use the MATLAB Distributed Computing Server to scale up our applications, let me show you the specific steps that I took to get here. First step is you prototype your code with the Parallel Computing Toolbox on your desktop. Even with a basic desktop or laptop, you can use the Parallel Computing Toolbox syntax and get your algorithms up and running. Note that the Parallel Computing Toolbox provides the infrastructure for copying files to the worker, adding additional paths, monitoring jobs, and retrieving the results. Your second step is to get access to an enabled cluster. For clusters at your own site, you will need to ensure that your cluster administrator has installed and integrated the MATLAB Distributed Computing Server. Once your code is working and you have access to a cluster, change your cluster profile on the client system to use your computer cluster. You can import the profile directly through the parallel menu in the MATLAB toolstrip. After you have changed the profile, when you execute parallel computing syntax from your client session, your computations will be made with the cluster hardware. There are a few primary reasons to move your Parallel Computing Toolbox workflow from a desktop computer to a cluster. You might want to perform computations on a cluster to free up your desktop computer for other work. You can submit jobs to a cluster and retrieve the results when they're done. You can even shut down your local computer while you wait. You can also use a cluster to scale an application that you have developed on your desktop. Getting computations to take minutes rather than hours allows you to make updates to code and execute multiple runs all in the same day. And if you have an array that is too large for your computer's memory, you can use distributed arrays to store data across multiple computers, so that each computer contains only a part of the array. A growing number of MATLAB matrix operations and functions have been enhanced to work with distributed arrays using the Parallel Computing Toolbox. These enhanced functions allow you to use your desktop session to operate on the entire distributed array as a single entity. With our parallel computing tools, users can create, monitor, and retrieve data from jobs all directly from MATLAB. Even if your desktop code does not use parallel computing, you can still use batch to submit your workflow, whether it is script-based or functions. MATLAB even provides the infrastructure to automatically copy the files needed to run your workflow. There is no need to learn Unix or Windows-specific submission syntax or to build a framework for submission and retrieval. And if you're using parallel computing within your code, you can also scale your submitted workflow with a pool of MATLAB workers. Let me show you an example of offloading work with batch. What we have here is a MATLAB script that contains all the steps necessary for the submission, retrieval, and post-processing of our algorithm. And if you guys take a look at this particular section of code, I'm defining the batch object, and the only things I need to specify are the name of the function I'm going to call. This function is going to return 5 outputs. These are the inputs for that function, and if I want to run this on a specific cluster profile, and how big the pool of workers is. So I can specify if I want to run this locally on my machine, or if I want to use a different number of MATLAB workers, I can easily do that. So let's take a closer look and let's step through the code. So let's minimize this so that we can see what's going on. So let me run the first section of code. Nothing really happens here. In this particular section of code, I'm making sure that if I have an interactive pool of workers, that I close it so that the workers are available to run the simulation I'm trying to run. And in this section is where I am actually going to submit the job to be executed. So I'm going to be running, submitting the job. I can see that a job object has been created. I can check the status of my job interactively. And if you guys notice, my job is running, but I don't get the busy sign anymore. So my MATLAB session is free for me to do operations while the job is still running in the background, because now this job is actually running on the cluster side, is not using my local MATLAB session. I can also monitor the status of these jobs interactively if I want, so I can take a look and see that the job that I just submitted, it just finished. So I can check to see if they're still running, if there was an error message. I can do that programmatically as well, but if you wanted to do that interactively, you can easily get that done. Now that we've done that, let's retrieve our results. So you can choose, for example, to wait for your job to be done. Let's say you want to get the results the second your job is completed, so you can just say, hey, wait for my job to be done, and when it's done, then move on. In this case, it's already finished, so it's not going to wait for it. And now I'm going to go and get my outputs, so I can do that very easily. Just get the outputs from my job and post-process it, so we can see that we're getting exactly the same answer that we're getting before, but we get even further speed ups by using additional hardware at our disposal. Now let's say that I want to run an even larger simulation. So I have another batch job. The only difference with the previous one is that I'm using a much larger number of combinations. So this problem is roughly 156 times larger than the one we just ran a second ago. Unfortunately, we don't have time to run this larger simulation live, but I did run it offline with different numbers of workers. Let me show you what I got. Okay, here's a benchmark with the results I got. If I use, for that specific problem size, if I use only one worker, it takes 187 minutes to complete. But if I increase the number of workers, I can see how the computation time gets reduced. And when I get to 160 workers, I can see that my application is 118 times faster, which is really, really good. Okay, the MATLAB Distributed Computing Server uses a dynamic licensing model that accounts for both MATLAB and toolboxes. The only licenses that are checked out are distributed computing server licenses, one worker for each computational engine used. To ensure that your desktop code runs on the cluster, the dynamic licensing model gives you cluster-side computation engine access to use any compatible toolbox that you could access from your desktop license. The server does not check out any toolbox or MATLAB licenses on the client side, so you don't need to worry about taking resources away from your or anyone else's desktop session. And for non-interactive jobs with the distributed computing server, you can even exit your MATLAB session after your job has been queued and then retrieve your job at a later time. For the workflows that I've shown today, you need the following: MATLAB and the parallel computing toolbox, access to an enabled cluster, and a license for the MATLAB distributed computing server. And note that the server version should match the parallel computing toolbox version. In this presentation, I've shown you how easy it can be to use cluster hardware with your MATLAB workflow. MathWorks provides tools and infrastructure to let you prototype on the desktop and extend your workflow to the additional hardware.